الخير جميعا. Good evening, everyone. In the name of the Arab Physical Society and the Center of Theoretical Physics and Astrophysics, I would like to welcome you all to this important lecture. First, our speaker is Dr. Xavier Dupac. He was born in 1976 in Limoges, France, and he got his PhD in astrophysics, summa cum laude, at the University of Toulouse 3 or Université Paul Sabatier back in 2002. He has actually a long employment history. So the most recent ones are the Planck archive scientist at the European Space Agency until 2017, and in 2016 and until now at the Euclid Science Operations Scientist at ESA, the European Space Agency as well. He has also a long list of coordination and management experience. For instance, from 2023 till now, he's the coordinator and chairman of the Euclid Survey Working Group. He's responsible for defining, implementing, and verifying the Euclid Survey. And before that, from 2016 until the present, he's the product owner of the Euclid Survey System. His scientific experience is so varied as well. He has already 300 publications in cosmology and the interstellar medium, and 81,000 citations. Wow. From 2000 the year 2000 till now, he participated in more than 40 international conferences in cosmology, interstellar medium, and space science. And he's so active at the outreach level. For instance, he has numerous interviews for Euclid on TV, radio, and press, and for Planck as well. Planck on TV, radio, and press. He and the group, of course, he received several awards. For instance, the Gruber Cosmology Prize in 2018, the Planck team, and the 2018 Royal Astronomical Society Group Achievement Award, the Planck team, and the 2019 European Physical Society Prize to the Planck collaboration. Okay, so you are welcome, Dr. Xavier. Please, we need your voice muted.
Hi, thank you so much, Hannah, Professor Sabat. I'm really happy and honored to be able to give this this talk today. So thanks a lot for the invitation.
Our pleasure. Our pleasure.
Thank you. So okay.
Do you want to share some slides?
Yeah, I will share now. Wait a second. How do I share with this? Yeah. Okay. This one. Just want to put it in the presentation mode. Okay, can you see the slides? Okay. Okay, so thanks everyone for joining this presentation. I will try to give you a brief history of the universe, its origins, present and future. So it sounds like a lot, but I think it's also quite spectacular that, in fact, it can be understood by us in a lot of ways. It's not actually that difficult to picture the history of the universe and the way the universe works as we understand it today. This is really quite remarkable, I think. The summary of my talk, it will be essentially divided in three parts. The first part is a very brief history of how we get to what we know today. So our understanding of the universe from antiquity until now, with only the main milestones, of course. The second part of the talk is really describing what is the modern view of the universe today with physical cosmology and its evolution from what we call the Big Bang, the beginning of the universe as we understand it, until today. And the third part will be dedicated to what happens next, to the future of the universe as we think we can predict it from the science that we know nowadays, and the question of its ultimate fate. Just want to mention that these two images are from the James Webb Space Telescope. It's quite spectacular. You can see many galaxies in there with many different time and evolution state of these galaxies and age of the universe. So this is, I think, quite beautiful already, these images. Okay, so just going to the first part of the talk. So how do we get there? So you know that in antiquity, we had this view of the universe. It was the Ptolemaic system. It was the dominant view at the time. It continued to be the dominant view until the late Middle Ages. And actually, it was, as you can see here, there was the Earth in the middle. The Earth was the center of the universe, were gravitating around the Earth. So first the Moon, and then the other planets, so Mercury, Venus, and then the Sun was between Venus and Mars, of course, the place that the Earth has, in fact, today. Then Jupiter, Saturn, that were all, was the okay, it's just muted. Sorry. Okay. Then after Saturn, so the other planets were not known at the time. Uranus and Neptune were not known. Excuse me? Can you hear me?
Go on.
Can you hear me okay? Yeah. Okay, so since I heard something, I didn't know if you could still hear me.
There was
okay.
There was some interference, but it's okay.
Okay. So the view was that the Earth was spherical. So contrary to a popular belief, it was never really believed, at least by people who were literate, that the Earth was flat. And that was more like a common misconception of what the knowledge was in the antiquity and the Middle Ages. So that the Earth was always considered spherical, but it was at the center of the universe. And beyond these 7 moving objects that I just mentioned, everything there was supposed to be fixed and perfect, because at that time it was not possible to detect the motion of the stars. So the stars were fixed, and everything was immutable, everything was just not moving at all. And so this was considered something divine. So this was like the domain of the divinity was beyond the spheres of the planets. And then, as you can see also on this Portuguese view of the world, it was written in Latin that it's the place where the sky and the angels were. Okay. And then at some point, so in the 16th century, there was this guy, Copernicus, who claimed for the first time, at least, that was probably not the first time that someone thought about it, but the first time that it became really public and it made a lot of fuss, that it was simpler and actually more logical to put the sun in the middle, put the sun at the center of the universe. And then you had the Earth as the third planet from the sun. And so this was a simplification of the model. So it's very important to remember that it was really something that was not really a discovery, but simply a change of paradigm due to applying what, in modern terms, we could call the Occam's razor. So Occam's razor tells you, well, in science, normally, if you have 2 or more explanations possible for the same thing, the simplest explanation is often the right one. In this case, well, it turned to be true, right? I mean, that was simpler than the Ptolemaic model, and it was also true. In that model, the last circle is still the fixed stars. Okay, so this there's no change. So the view of the universe is that of what we know today to be the solar system. And beyond the solar system, it was supposed to be one big sphere filled with stars. Maybe it was like I've just unmuted. Can you hear me now? Okay. So yeah, so the size of the universe at that time was still limited to what we know to be the solar system today, or actually a rather small part of the solar system. Okay. Okay. Then a few more milestones I want to mention. So in 1718, we had this important discovery by Halley that he made some measurements of the proper motion of some stars. So then the scientists then really realized that this famous perfect sphere was not perfect. It was actually moving. So stars became to be, starting to be considered as also moving objects and not something different. And so the idea of the fixed perfect background celestial sphere started to crumble at that point. And then I'm going really quickly, but just to give you what I think are the main milestones in this understanding of the universe. So in 1838, we had for the first time the direct measurements of the distance to a star by Bessel using the parallax technique that some of you may be familiar with this. And that was actually demonstrating the vast separation of stars in the sky. So the distances involved were really greater, much greater than the distance of the planets to the sun. So at that point, it became clear that the universe was a lot bigger than what was thought before. And then again, in 1924, there was again this milestone that the existence of external galaxies actually was demonstrated first by Hubble beyond our own Milky Way, our own galaxy. So again, the distances involved are a lot larger than that of the interstellar distances. So this was, again, a revolution in the sense that the true size of the observable universe is little by little discovered. So more and more galaxies are discovered, and the size of the universe clearly becomes understood to be much larger than what was thought in the previous centuries. So again, another very important discovery is that in 1917, Vestal Schleifer discovered that most of the galaxies that could be observed actually were redshifted through the Doppler effect. So actually, he was looking at the lines of some atoms and seeing that these lines were shifted towards the red, so toward longer wavelengths. And this has to be due to the Doppler effect. That means that the galaxy is actually receding from us. So if you have galaxies moving around in the universe, you could expect that if the universe is static, then of course you could expect that some of them are redshifted and others are blue shifted. But that you don't see. That you see only on the local group of galaxies. And actually, if you look at the galaxies beyond that local group, well, you see that they are all receding. Okay, they are all redshifted and receding from us. So this is very difficult to explain with a static universe. And this was the first hint at an expanding universe, as we understand it today. We understand that the space is expanding. Then another important milestone was in 1964 when Penzias and Wilson discovered, a little bit by chance, the cosmic microwave background. So that was really the definite proof that the universe was in the past very dense and hot, because this is something that you get if you had in the distant past, a universe that was in the state of a plasma. Okay, so if plasma, and when the plasma becomes a gas, atomic gas, at that point there is this light that is emitted, that is the cosmic background. So this was also a very important milestone, and the first real smoking gun for the hot Big Bang hypothesis, that the universe started in a state of very dense and hot. So today, our picture of the physical universe is that of an ever-expanding space, starting from a very hot and dense hypothetical birth, conventionally called the Big Bang, a little bit as it started as a joke, and this expression of Big Bang is not really a bang, but it's something that can be the beginning of the universe. Actually, we don't really know if this is the beginning or not. Let's say the simplest possible explanation given the data. So very important to remember also that because the speed of light is finite and the distances are so great in between galaxies, so looking far away also means that we are looking into the distant past. So here you have what I find to be a very nice picture of the universe. So you start with the solar system here, and you go to the stars, the Milky Way, and okay, and then you go into the galaxies, then the super clusters, different kind of great structures. Galaxies until the horizon that you have here, this cosmic microwave background, is the first light emitted freely in the universe. So this is what we call the observable universe. So this is a very important concept. We can only observe the closer parts of the universe, since light speed is finite, and light travel time is limited by the age of the universe. So the light has been able to travel to us until from the CMB, from the cosmic background, until now. So it's a finite amount of time, and the distances are so great that this is what limits our understanding of the universe. This is what we call the observable universe. It's limited by this horizon. And it is understood that the complete universe in this understanding has to be much larger than the observable universe and could even be infinite. But this is not something that we have direct observational access to. So we cannot have direct evidence of the true size of the true complete universe. Okay, I will come back to that. All right, so going now into the second part of the talk, the modern view of the universe, so evolution from the Big Bang until today. So, as I said, the Big Bang is conventionally considered to be the beginning of time, as we have no concluding observations whether there was something before it or not. Here you can see on the top right here the schematic view of how the universe evolved from the Big Bang. So you first have these quantum fluctuations, and you have this inflationary period, and you have the CMB, and you have evolution of galaxies, and so on. And I will describe this in the coming slides. What is very important to remember concerning the Big Bang is that it's space itself that is expanding. So it's not an explosion. Okay, it's not normally when you speak to people about Big Bang, they have this picture that it's an explosion, so there's something exploding in a pre-existing space, and that is not the case. That is really the space itself that is expanding, and the density of matter and energy has always been very homogeneous from the beginning in the whole universe. Still today at large scales, at cosmological scales, the universe is very homogeneous. Okay, and the limit of our understanding in the past starts really at that point, 10 to the minus 43 seconds. Before that point, we have actually really no idea what's going on. That's what we call the Planck epoch. This time is dominated by quantum effects of gravity that dominate the physical interactions. And this is, well, something that there is a lot of theoretical work being done, but this is really something where there is very little understanding. We have no physical device that can reproduce such huge amount of energy and densities and temperatures. So this is basically unknown. Then we have what we call the grand unification epoch, up to 10 to the minus 36 seconds after the Big Bang. So during this time, what happens physically is that the three fundamental forces, so electromagnetism, strong interaction, and weak interaction, separate at the end of this period. So before that, they are kind of united. After that, we have the fundamental forces of nature that are there as we know them today. So they're already there. So early in the universe, 10 to the minus 36 seconds, we have the fundamental forces more or less as we know them today. And then what happens? Interesting things. So we have this cosmic inflation thing. So this is something happening up to 10 to the minus 32 second. This is a huge increase of the volume. the space of the universe. It's inflated very quickly, factor about 10 to the 26. And the universe then is cooled from 10 to the 27 to 10 to the 22K. And this is something that is a bit also mysterious, but it's necessary to invoke this to explain some of the properties of the universe. And well, basically, after inflation stops, then the universe continues to expand, but not so quickly, and to cool. Cosmic inflation is needed, to help explaining the extreme homogeneity of the early universe. Otherwise, it's very hard to figure out how this could be possible. And then what happens in the next instance of the universe? So up to 10 to the -5 seconds. That's what is called the quark epoch, because this the fundamental particles were free in a kind of quark gluon plasma, right? So these are fundamental massive particles that exist separately from each other until the protons and neutrons can form. This happens after this period. And so by about this period in the first second, the universe has cooled enough for hadrons, that is protons and neutrons, to form. And these will be later, you probably know, the bricks to form atom nuclei later on. So at that early stage of the universe, there was these protons and neutrons, and of course electrons going around in the plasma, together with the photons in the plasma. Okay. At 1 second, we have the neutrino decoupling. So neutrinos cease to interact with baryonic matter and start flying freely in space. And this is very important milestone, let's say, in the history of the universe, because this is the first background. This is the first time that, at least that we know of, that an observable particle can freely float and freely go and cross the vast distances in the universe. And that's what is called the cosmic neutrino background. Unfortunately, this background is extremely difficult to observe today because neutrinos are extremely difficult to observe in the first place. They are not interacting very much with normal matter. So even neutrinos coming from the sun, we can detect them. It takes a lot of very big detectors, like a lot of water to detect neutrinos coming from the sun. And those ones coming from the beginning of the universe are actually extremely lower energy and so extremely more difficult to observe. This is not something that we think we can observe in the next couple of decades at least, but this still is a very interesting thing to keep in mind for the future. After that, so during the period 10 seconds to 20 minutes, so this is the very important period that where the Big Bang nucleosynthesis occurs. So this is when the first nuclei are formed. So from the existing protons and neutrons, you get the simplest elements formed. So as you can see here in the periodic table, so hydrogen, helium, and some limited amount of lithium and the beryllium. So the elements number 1, 2, 3, 4. This is the number of protons: 1 proton, 2 proton, 3 proton, 4 protons. These are formed in great number during the Big Bang nucleosynthesis, especially helium. Helium is really the very abundant element formed in this period. And as the universe continues to expand and cool, these elements are not stable. Okay, and then we have this very long period, let's say, compared to what happens before. That is up to 370,000 years. That is the photon epoch. So the universe is a hot plasma of nuclei, electrons, and photons. So it's a plasma. There's no free light coming out of that. And then happens something very, very interesting. Okay, so during this epoch, the temperature continues, of course, to cool. So the space expands, the density of the matter and energy decreases slowly, and the temperature also decreases. And until it reaches 4,000 K, the universe is a plasma. And at the end of this epoch, the first combination of atoms occurs. Note that normally it's normally called in the literature recombination, which I find ridiculous because it's the first time it's done, so it should be just called combination, I suppose. Yeah, so I call it combination, but you will always find in the literature this called the recombination. So just that you're not surprised. So the nuclei, so essentially hydrogen and helium, are then combining with electrons to form atoms, neutral atoms, and this emits also a lot of light. And you may wonder why you have this funny orange rectangle here. This is not in homage to Donald Trump at all. It's simply because this is what you would see in the universe if you could be there at that time with your human eyes. You would see orange light filling the universe in all directions, right? And this is what we know today as the cosmic microwave background. We call it microwave because now it is in the microwave. At the time it was in the visible light, it was orange, but it has cooled since then, and it has gone into the infrared and then the microwaves. So this is what we have measured a few years ago with Planck, and this is the full map of the full sky and all the fluctuations of the temperature of the cosmic background. And this is really quite beautiful, I find, because this is really the whole sky. So the data here, normally you have the galaxy in the middle, our own galaxy, and you have some other things. You have the dipole that is due to the motion of the Earth around the sun, and so on. But once you subtract these components, what you're left with is this. And this is really the first picture of the universe. It's really the first light that you can see. You cannot see beyond that, unless one day you could see the neutrino background, but with electromagnetic waves, with light, that's the earliest you can see. And what you see is the very small inhomogeneities that look a bit boring like this, but they have a lot of information, in fact, about the universe and about its characteristics. Yeah, so that's just what I said before. These anisotropies can be studied to constrain the cosmological parameters, such as the density and age of the universe and its contents, such as, well, mostly bionic matter, dark matter, and vacuum energy, also called dark energy, etc. Yeah, as I said, this is the oldest light we can observe in the universe. Okay, and now this is what you see after that, right? Because once the CMB is emitted, so the universe continues expanding and cooling, redshifting the CMB to red and then infrared. So if you were a human, then after a while, what you would see is this, just darkness. No visible light anymore in the universe, just black. And the CMB is now in the infrared. Yeah. So unless you have infrared eyes or goggles, you will not see anything else than this. The universe becomes dark to a human eye. So that's why we call this period the Dark Ages, starting roughly at the time of the CMB, a bit later, in fact, until a period that we don't really know when exactly, something around probably 150 to 200 million years. Why? Well, that's because something happens then. Until then, the matter in the universe is made of basically atomic hydrogen and helium. And the small inhomogeneities originated in quantum fluctuations in the very early universe are starting growing into overdensities and underdensities of the gas. This is due to gravity, simply. Gravity is always attractive. So gravity tends to gather things around overdensities to create more dense areas. And the voids become even more empty, let's say. Okay. So actually, this is a recent discovery that you can see from the James Webb here on the right, because what gets us out of the dark ages is that what we call the reionization of the universe. And this occurs when the first stars are formed, first stars and galaxies that are just a group of stars. Okay, so here is a recent discovery made by James Webb when they have this very clear line discovered here at something like 1.80 something microns. And this is quite crazy, right? In the ultraviolet, if I'm not mistaken, and so it's extremely redshifted, right? So this is 14.32. So this is up to now is considered to be the oldest galaxy discovered. Okay, so this is quite remarkable. So this is, yeah, as it's written here, current research shows evidence for first stars at about 14 in redshift, so about 300 million years after the Big Bang. It's not very clear whether we will be able to find galaxies and stars earlier than that. If we do, then it would even be before that date. And what happens next? So over the cosmic time till today, so 13.8 billion years, giga-years, stars form and die, and galaxies form and evolve into larger and more complex ones. And from these individual galaxies, also larger structures can form. Galaxies can gather into galaxy clusters, then superclusters, and forming filaments and voids, forming all the large-scale structure that you can see here at the bottom here. A simulation of a part of the universe where you can see clearly these filaments and the voids, and then the way all these large-scale structures of galaxies are evolving with cosmic time. Remember that at the beginning of the universe, everything was so homogeneous. The CMB, the inhomogeneity that you can measure on the CMB surface are, in fact, 10 to the -5 compared to the background. So it's extremely homogeneous. Today, it's not so homogeneous, at least at this scale. If you go to larger scale, it will become more homogeneous. Yeah. Okay. Now we live in this period where we have stars, we have galaxies, so that's what we call the stelliferous era. So when stars form, evolve, and die. You can see here a simplified view of what happens. So you have a nebula of gas and dust forms a star. So there are different masses possible for a star. There are rather small star here on the top and a larger star on the bottom here. After they evolve, they become giants, red giants, so on. Then they explode. They become planetary nebula, as it's called. It's nothing to do with planets, but this is something historical that stocks, right? And then becoming a white dwarf. And when they are big stars, they become red supergiants, and then they explode in a different way into a supernova. They can become either a neutron star or a black hole. I will also come to that. What is also important to remember is that this cycle of life of stars is actually something that allows the heavy elements to form in the universe, as you can see here at the bottom. Okay, so yeah. So basically, stars are long-lived thermonuclear bombs, let's say. They are transmuting light elements, such as helium and hydrogen in the beginning, into heavier ones, such as carbon, nitrogen, oxygen, iron, and others. So you can see that at the bottom here, basically a lot of elements are created in the normal stars, as the case for the one here in green. And for other elements is mostly into massive stars. And for actually a lot of rarer metals, it's due to even more exotic things like merging neutron stars or exploding white dwarfs. So it's quite complex, but essentially this is the whole life of the stars that allow these elements to exist. And of course, these elements are necessary to form planets, especially rocky planets like ours, and then, of course, life. Now, you cannot have life with just hydrogen and helium. So we can thank the stars to have been going through all this cycle of evolving and dying and then reforming with different elementary composition for the next generation of stars. Yeah, and when the fusion gas is exhausted, so it's a thermonuclear reaction. So what happens is that the hydrogen, let's say at the beginning, it's hydrogen and helium. So this fusions into heavier things such as carbon. And once this is completed, once there is no more gas to fusion, what happens is the radiative pressure stops. And then the star has nothing to sustain it anymore. So it collapses under its own gravity. Remember that gravity is always attractive. So if there is no pressure to balance gravity, then gravity wins. And so the star collapses. And what happens is that it becomes, depending on its initial mass, it ends up producing different stellar remnants that can be white dwarf, neutron star, black hole, depending on the mass of the star, of the initial mass of the star. Okay, so I've described more or less what we are living today, the Stelliferous era. Now I'm going into the third and last part of the talk, that is what happens in the future. Okay, so the first big milestone will happen about 10 to the 14 years in the future. So it's a long time, since now we are about 14 billion years from the Big Bang. It's about 10 to the 10, so it's only 1 in 10,000 of the total time of the Stelliferous era. We are just at the beginning of this era. So at that point, all the gas in all the galaxies have been used in stars forming heavy elements and stellar remnants. So this is the end of the Stelliferous era. So the mass is now locked into white dwarfs, neutron stars, black holes, and planets, and dark matter. I haven't talked much about dark matter so far, because essentially dark matter is something that does not interact with light at all. So that's why we call it dark, even though we should call it really transparent matter. But it's there since the beginning. It's slowly interacting with itself and with other mass, with baryonic mass, just through gravity. And yeah, so let's say it doesn't really evolve beyond the becoming denser, and yeah, it doesn't really do anything special that we know of. Another mysterious component of the universe, you can see in this chart pie here, it represents 68%, what we sometimes call dark energy, or that I prefer to call vacuum energy, because I think it describes more visually what it does. So this is something that accelerates the expansion of space. And because of this, the expansion speed goes beyond what the initial kick from the Big Bang does. So from the Big Bang, the universe starts to expand, but then gravity starts pulling it against the gravity goes against the expansion. So if it were only up to gravity, the universe expansion would be always decelerating. It's not the case today, actually. What we have been able to measure is that at some point in the past, there is this inflection point between the slow expansion and the accelerating expansion. And this cannot be explained without this mysterious component of vacuum energy or dark energy. Here, so our current understanding is that the vacuum energy will continue to accelerate the universe expansion forever, even beyond the end of the Stelliferous era. So at some point, as I said, there is no more fuel to burn into stars. So what you get is a universe made of degenerate objects. So this is from 10 to the 14 to 10 to the 40. Degenerate, they are called degenerate not because of their morality or anything, but because they are made of degenerate matter. So it's a kind of matter that is sustained by quantum pressure, either of electrons in the case of white dwarfs, or of neutrons in the case of neutron stars. In principle, there's no more stars, no life in principle to live anywhere, unless, of course, you can imagine extremely advanced civilizations that would be able to cling to some strange way of tapping energy onto white dwarfs or something, but that will require a lot of technology. So it's a very hypothetical thing. Okay, what happens next is really uncertain. So it depends on whether protons decay or not. So I want to say one thing here, because these three images here, they are representing respectively here white dwarf. So this is an image. This is neutrons. This is an image of a neutron star area, and this is actually the first image of a black hole. That is an actual image. It's not a simulation. Because this is from the galaxy M87 central black hole. It's a supermassive black hole. It's really quite spectacular. It's from a couple of years ago, I think. It's really spectacular to see this central dark area that is indeed a place where the light cannot get out. So this is a real view of the black hole. Okay, what happens next depends on the protons decay or not. So if the protons are decaying, then a reasonable hypothesis is that it decays in about 10 to the 40 years half-life. In this case, so at that point, all the matter, including planets, white dwarfs, neutron stars, will have decayed into photons and leptons, that is mostly electrons, except the black hole. So this is then a universe that is dominated by black holes, black hole era. This black hole era is supposed to last for an extremely long time. So from 10 to the 40 to 10 to the 110 years. So at that point, black holes are the only remaining, let's say, mass of the universe together with the dark matter. There is no more baryonic matters, no atoms, only electrons, neutrons, and photons floating around. And the vacuum energy continues to accelerate the expansion. And the universe continues to expand and cool. So you have to understand that in our understanding of the universe with the equations we have today, there is really no reason that this expansion stops at any point, that this acceleration stops. I mean, the vacuum energy tends, if it's as simple as we understand it today, it's just something that that grows with volume, right? So the more space there is, the more dark energy or vacuum energy there is. So it contributes to accelerate even more the expansion, and that forever. But that is our understanding today of the vacuum energy. That's also something that we are trying to understand better. Okay, so continuing on the black hole era, so there is no more visible light. The universe is back into darkness as during the Dark Ages. And then there is something really quite funny appearing, that is that the black holes are not immortal themselves. They will slowly evaporate through what is called the Hawking radiation. This is a quantum effect that allows particles to escape the event horizon of the black hole. By the way, you can see here another image of a black hole, this time of our own galaxy. This is the one so-called Sagittarius A, the supermassive black hole of about 4 million solar masses at the center of our galaxy. That's right, we have this monster at the center of our galaxy. But we still have time before this guy sucks everything around it. And so for supermassive black holes, they are the ones that need more time to evaporate. So those ones need 10 to the 100 years, which is, of course, an unbelievably long amount of time, but still not eternal. So after this, essentially the universe will be in a state of heat death. So essentially nothing more happens. This is called the dark era. Gravitationally, at that point, the universe is dominated by dark matter and electrons. So normal black holes, only remaining matter is dark matter, even though that, again, we don't know what it is, we don't know how it evolves, if it does, at very large time scales, so this is quite hypothetical. So we don't really know if dark matter will also evolve into something else, or also evaporate or whatever. Everything is, I mean, people can theorize on this and imagine many things. And then, yeah, so time becomes meaningless because entropy is maximum and there isn't just basically nothing happening anymore. Now, as you can see here, I mean, it's a log scale here. You can see basically what the different epochs are. You can see the different times. In terms of logarithmic scale here, you see that the Stelliferous era, the time where we live in, is quite short. It's really short, even though in absolute time it's more than the primordial era, of course. But if you look at this log scale, it is very brief. So that the time during which you can have stars and planets and life in your universe is really quite small, especially compared to what happens next. Though an interesting question we can ask in this picture that we have today of the evolution of the universe is eternal darkness and coldness the ultimate fate of our universe? And actually the answer is no. Most certainly not. It's actually very difficult to think that it could be the case because of our savior. Again, it's quantum physics. It's quantum fluctuations. So what can happen is the universe could avoid eternal heat death through random quantum tunneling and quantum fluctuations. Why? Because, so you know, quantum fluctuations happen all the time. And they're basically random. And so there is actually a non-zero probability that at any point in the history of the universe that a new Big Bang happens spontaneously. Now, of course, the probability of this is extremely low. So if you want to calculate the probability, let's say that all the molecules of air in your room suddenly will be concentrated in the same corner of the room, it will be an extremely low probability, but still it will be non-zero, right? So in the case of a new Big Bang, it's an even lower, much lower probability, but still non-zero. And when we're talking about infinitely expanding universe forever, then of course non-zero probability means that it will certainly happen. And so this understanding at the moment, so there was some interesting studies there that estimating this probability that a new universe, a new Big Bang is created in roughly this number that is just impossible to imagine. It's 10 to the 56 years. It's but it's still not eternal. So yeah, this is a bit our understanding of the future of the universe today. I want to mention again that in case the proton does not decay, the picture is a bit different. Okay, then the neutron stars and so on can maybe live a lot longer, even planets. But still, at the end, it still goes into the black holes, but with a lot longer time. Okay, so it's a bit different picture, but yeah. There are what I want to say to conclude, let's say, is that there are still many uncertainties. Okay, what I presented is let's say the dominant view of the physical universe today. There are still many uncertainties, notably concerning the nature of dark matter and that of vacuum energy or dark energy. So the more we study these things, the more we will be able to refine our view and maybe even to change our understanding of cosmology. Another big question that is still not completely closed is the geometry and size of the universe. The measurements that are done, especially the ones we did with Planck recently, show that the space of the universe is very close to a flat geometry, also called Euclidean geometry. So flat geometry means a model of an infinite universe. So to convince yourself of that, you have to go into the two-dimensional analogy of the three-dimensional space. Imagine a tablecloth, for example. A tablecloth, only the table has no limit. The table is infinite, right? That's a model of an infinite universe. Now, if the curvature of your table is slightly closed, just a little bit, then you understand it's not infinite anymore. It will be in the shape of a sphere, and it will be finite. So we don't know actually if the total universe is finite or infinite. We're not sure. Because we're measuring that we are exactly or very close to the critical density. So still everything is possible in there. And of course, understanding whether our universe is finite or infinite may have vast philosophical implications. There's also another question that is something that you probably heard in many occasions, and that of the multiverse. So the multiverse is an interesting hypothesis. So it says that there are not just one universe, but many universes, maybe an infinite number of universes out there. And this is often invoked to avoid the strong anthropic principle. So strong anthropic principle tells you that, yeah, the universe is tuned so that it allows the emergence of complexity and life, and ultimately advanced civilizations like ourselves, if we can consider ourselves advanced. I don't know, but yeah. So if you want to avoid the strong anthropic principle, some people want to try to avoid that because they consider that, well, it's kind of putting God in the middle again. And some people don't like that, others like that. But so some people say, no, there is no reason to invoke the strong anthropic principle. We live in just one universe that happens to be the one or one of the few that are compatible with our existence, but there is an infinite number of other universes with completely different parameters out there where there's no life. So we just happen to be observing from where we are. So that's the weak anthropic principle and not the strong one. So, by the way, just to mention that, I think clearly there is no reliable data so far on the existence of the multiverse. So this is just like, okay, speculation and philosophy, but still very interesting, of course. There are also a lot of ideas about hidden dimensions and so on, but yeah, I will not get into that. I just want to finish with showing you these images from Euclid, because this is very new, and I think this is really beautiful. This is the mosaic that we did with Euclid. So this is 1% of the extragalactic sky that we are going to observe, so about 0.3% of the full sky. And what you can see here is quite beautiful. I think you see many galaxies already. You see these bluish filaments. This is actually from our own galaxy. This is the foreground. So this is something that we don't like to see as cosmologists, because we are interested in what's behind that, but it's still beautiful, I think. And you can see many galaxies there in different colors. So the redder ones are the ones that are farther away. Well, they're redshifted, so they're farther away, basically. If you zoom in, you will see many things. Like here, you can see this zoom into a galaxy cluster. So you can see this beautiful, for example, these beautiful spiral galaxies in there. You see that there are so many galaxies in there. It's really spectacular. So this is only 1%. That what hopefully we will get in 6 years. So yeah, stay tuned, and from all these galaxies, we will be able to understand better dark energy, vacuum energy, and dark matter. Why maybe you know, what dark energy does, if it really stays the same over cosmic time, or if it evolves. So understanding better these things will help us to understand better the history of the universe and its future as well. So yeah, more cosmology results soon coming from ESA. Next year already, there will be a first delivery of cosmology results. So stay tuned, and yeah, thank you so much for your attention. I will take questions if you want. Thank you.
Oh, thank you so much, Xavier Dupac, for this wonderful presentation. I don't know why my image is, oh, okay. Thank you so much for this wonderful presentation. I really enjoyed it with this journey through time and space. But apparently the future of our universe is rather dark, unless, of course, we some of predictions come true, other predictions about which we are not certain. Anyhow,
Yeah,
now
it seems boring.
we have room for a few questions among the audience. Anybody has a question, he or she may raise their hands. I will put question. Possible. Listen, I have a rather, let me say, philosophical problem with our basic subjects, okay, especially in physics, astronomy, and cosmology, especially when it comes to the dark side, the dark energy and dark matter. The amount, the amount of dark matter and energy may reach up to 95 or 96%, right, out of the total mass of the universe. Now, my question is, when we speak about our understanding of the universe based on this 4 to 5% of the total, so how confident can we be about our understanding while most of this of our known universe is unknown, actually? It's 95% of it. It's still unknown. Don't know the nature, neither of dark matter nor of dark energy. So isn't this, philosophically speaking, isn't this problematic, really? See what I mean?
Yeah. Yes, I mean, I think you're right. It's a view of the physical universe that is based, as you say, on the 5% of its energy content. Still, what we know, the little that we know about dark matter and dark energy is that they're a little bit more boring components, let's say. So we think that we understand them a bit, in the sense that we understand the way they influence the normal matter and energy. So for example, dark matter is dominant in terms of mass, so that's where the galaxies will fall into the dark matter wells and so on. So we understand what it does on gravity. We think we understand something like this. So in terms, okay, for vacuum energy or dark energy, well, we see that there is this effect. So we attribute this effect to a component called dark energy, but actually And there are even other hypotheses. There are people who don't really believe in this mysterious form of energy, and they claim that, in fact, we don't understand the laws of gravity. So there is this modified Newtonian dynamic movement. Let's say that there are many, actually many scientists that delve into that. There's another way to try to explain this thing. But one way or another, we see that there is an acceleration. So we see that there is this mysterious component, and we have to continue to explore this. But you're right that our understanding of the universe could change quite a lot. In fact, in the coming decades, when we understand better these components.
Especially if I'm using a big if, if it turns out that instead of using dark matter, there might be some form of a modified version of gravity or dynamics, or who knows, right?
Yeah, it's a possibility.
Okay. Another thing I would like, can you give us just a brief idea about the Euclid mission?
Yeah.
I know we have seen some images, but what's the main aim?
Yeah, so Euclid, so this is a space telescope that we launched in 2023 in July, and it will be observing the sky for 6 years, at least. We hope at least the nominal mission is 6 years. And the goal is to observe many galaxies, so between 1 billion and 2 billion galaxies. And the scientific objective are twofold. So the one is what we call the weak lensing probe. So we're using gravitational lensing, but using all the galaxies that we can find. And with all this data, we can infer what we call the cosmic shear. So this is, let's say, a map of the way the dark matter in the line of sight is shearing the shape of galaxies, right? So by measuring the shape of all these galaxies, you can actually infer this global map of dark matter in the observed universe. So this is one of the probes, and the other one is that we are doing at the same time with the same telescope a spectroscopic survey. And the spectroscopic survey of galaxies is very good because it gives a very high precision on the redshift of the galaxies, because we have the spectroscopic redshifts that are the most precise way to get the redshift. So by doing that, what we can do is measure what we call the baryonic acoustic oscillation. So they are this kind of bubbles that are created by acoustic waves in the early universe. And that can be seen in the way large-scale galaxies are distributed around these bubbles, let's say. So this is the other probe. And so there are other probes we are going to use, also galaxy clusters and so on. And so the strength of Euclid is that there are really these different probes together that we can use to increase the knowledge on the cosmological parameters. The main goal in terms of cosmology is precisely on so-called dark energy, is really understanding whether it is just as was measured by Planck, if it's just a cosmological constant, or if it is something that also changes with cosmic time. So if it's measured that there is a change in cosmic time, then we'll see, because then you could imagine that in the future it is not as strong as it is today, or that is still to be discovered. So that's why I'm saying that, our view of the universe, on the future of the universe, could change, because depending on what we find on the way dark energy behaves, then it could change dramatically the picture that we have. So.
Okay, perfect. Thank you so much. We have 2 more questions. Start with the first one we raised his hand. Dr. Ammar Sakati, you ask your question.
Hi, how are you?
Hello.
I like your lecture, really. I like cosmology. I'm theoretical physicist. My question about
the Jordanian Astronomical Society.
Yes, yeah, thank you. I'm president of Jordanian Astronomical Society. Yeah, my question about, as you mentioned, about the multiverse. As we know, it comes from string theory and solution of Wheeler-DeWitt equation, the universal wave function, and we have sometimes we have infinite number of universes or something like that. All of these comes from theory, from models, mathematical models. But there's very weak experimental evidence. They said that there's blue areas in the cosmic background radiation. And somebody said that this is maybe a collision between our universe and other universe. There's a collision in the past, billions of years ago. It's not proved, and there's a lot of interpretations of the blue dot cold areas. This break down the homogeneity of the cosmic microwave background radiation. What do you think? Do you think, can we assume that this is a weak experimental evidence, or if there's any experimental evidences about the multiverse? I know from math, from models, we have it, but because observation is very important for us as a physicist.
Yeah, thank you very much for this comment. I think it's very important what you say, and it's yeah. So the blue spots in the CMB, indeed, these are anomalies that compared to the Gaussian random field that's explained by inflation and so on, blah blah blah. So indeed, there are a few things like that. There are these cold spots in the CMB. There are these anomalies to the standard model that are very interesting, and of course, people are getting very excited about them. And yes, and one interpretation, as you correctly mentioned, is that it could be due to a collision between two universes or brains, or I don't know what. I'm really not a specialist of that, so string theory. But this is obviously a very interesting, very rich theory, and necessary probably. So yeah, this is an interpretation that is possible. I mean, I don't know if it's really evidence of a multiverse already, but it could be a hint. So it's very interesting to pursue this research.
Thank you, Dr.
Thanks to you.
Okay. Thank you, Dr. Ammar. Next, we have a question from Mr. Muhammad Abdul Khalid. Please go ahead.
Okay. Hello. Thank you for the talk. It was really wonderful. My question is, for particle physics, we have the standard model, which basically kind of explains everything except gravity for sure. But for cosmology, I think the model we have is the lambda CDM. And is there any other models aside from this model, the lambda CDM, and what are the anomalies or deficiencies in this model? If the question makes anything sense.
Yeah, thank you. So I think globally the lambda CDM. So just to explain, the lambda CDM is basically the cold dark matter model. So it means that with lambda is the cosmological constant. So it's the simple version of the dark energy or vacuum energy. So this is what is let's say the best model so far. It's quite simple. It fits the data quite well. Of course, there are some areas as was mentioned by the previous comment. For example, the cold spots of the CMB that are not explained, they are out of the statistics. So you can always say that lambda CDM has some flaws because it doesn't explain absolutely everything. But in my view, to be honest, this is a model that has been standing for decades now, that is still on its feet, and my impression is that it's going to be very difficult to get rid of it. I mean, we are going to need really good data, very precise data, to actually give definite proof that something else is out there. And yeah, and I mean, again, so Euclid will contribute to that, also the James Webb and all the other projects, also the ground-based projects, and so there are many models. Yeah, I mean, there are many theoreticians working on alternative models. I don't really know all of the models that are out there, but many people are working on alternate models. One thing I mentioned before was the MOND, the modified Newtonian dynamics, is something that people invoke if they want to get rid of dark matter. I mean, there are many things.
Okay, thank you.
Thank you.
We have also Dr. Munib Eid from American University of Beirut. Please go ahead.
Well, I'm sorry, I had problem with Zoom, and then I have to reinstall it again. But I will listen to the recorded what you have recorded so far. I'm sorry, but I have a question. Is the dark matter model really reasonable to figure out what kind of stars will be formed after the dark age?
Sorry, I missed the last part. Is it reasonable for what?
Yeah,
Matter.
yeah. You know, when the dark age is over,
Mhm.
after recombination, there is about 2 million years dark age, right? Dark age means
200
infrared.
million years.
Yeah. So now there are these primordial stars.
Right.
We have research on that, the so-called population 3 stars.
Mhm.
So they are formed in the halo. The cosmological model is the dark matter model with a lambda, CDM lambda. Is that reasonable in your opinion?
Well, I think, yeah, I mean, the dark matter, I mean, the great advantage of the dark matter model is that you don't have to explain anything, right? Because everything that you see in gravity, you cannot explain with what you see with stars. You just say that dark matter is out there, right? So then you just have to try to explain why there is this amount of dark matter somewhere and not another amount. But so dark matter is invoked to explain the gravity curve of galaxies, also for globular clusters, for lots of things, and also for cosmological scales things, like for clusters. And so it's very flexible because it's just, since it's another matter component, you can have, let's say, almost freely the amount of dark matter that you need anywhere to explain your data, right? So I would say, I mean, dark matter is kind of practical. It's maybe some people consider that it's unavoidable because any attempt, let's say, to explain gravity without dark matter is bound to fail because it's just too complex and it just doesn't work. But I mean, I don't know. It's a great question. I think at the moment it's not really solved. I mean, whether really dark matter is real or not, but it happens to be probably at the moment the simplest explanation. But we know so little about it. So.
Yes, but excuse me. I mean, these first stars, they could be very massive, and they have exploded. You cannot observe them, so you have to. They are formed at redshift of between 20 and 30.
Okay, so that I'm not aware of this data of stars beyond.
But is there another model than the CDM lambda?
Yeah, I don't know. I don't know for stars that would be beyond Z20. So that would mean that you have, I mean, that somehow the overdensities have grown quicker than what we know. I don't. Yeah, that I don't know.
So this is the only model, okay, so far.
It's not the only model, but it's the one that fits best so far. Let's say.
That's what that we have.
Yeah, okay, fine.
The most acceptable model.
Yeah. You have to have a model. You have to have a model somehow.
Yep.
Yeah, well, I mean, okay.
Okay, we have another. Thank you, Dr. Eid, Munib Eid. We have another question from Mr. Abdurrahman. Please go.
Firstly, thank you for the amazing lecture or presentation.
Thank you.
My question is more practical wise. It was about how accurately can we measure the mass of black holes?
Okay. So the mass of black holes, basically they are inferred the same way that we can infer the mass of a star or any other body. So we see, for example, for black holes, what happens a lot is that we see stars orbiting them. So we know the type of stars, we know their distances, and we can measure the time it takes for the star to go around the black hole. So just by Newton's law, you can calculate the mass of the central body if you know the orbit, let's say, of
but
of
what
the
kind
star.
of
So by
black?
having many stars, you
Yeah, okay.
Okay.
Now there are stellar mass, black hole of stellar masses, and there are supermassive black holes. You have to distinguish between them.
of
So
course.
you can have an idea about the mass of if the star has, let's say, more than 30 solar masses, it will then collapse to a black hole. Okay, but what about the supermassive?
Yeah. So you mean how do they form?
Yeah, exactly. They
Yeah.
could be 1 million. They could be 10 to the 7. They are in the center of galaxies.
Yeah. So I think they're supposed to create
The big
more
problem, a big problem.
matter.
Especially with the observations of the James Webb Space Telescope, we observed supermassive black holes the very after in a very early phase of the universe, a few million years after the Big Bang. So that's really
Yeah,
problematic too, right?
or later in the galaxies. The
Yes.
galaxy, the center of galaxies, they could be deformed by, I don't know what the mechanism is, by coalescence of stars. I don't know. So it's very difficult to estimate the mass of the black hole if it's supermassive.
The same principle, right? I mean, it's dynamical argument that can measure even supermassive black holes. Can just measure the orbits of the stars orbiting it, and we get the mass in the same manner. But the formation issue is another question, how it forms.
Yeah.
Okay, let me see if there are any other questions. Again, we have Mr. Muhammad Abdul Khader.
Sorry, I just have a follow-up to just know if I got it right. So the lambda CDM just says or predicts that there are dark matter materials out there, but it doesn't provide any candidate or like WIMP or any other particle or candidates. So just throw the load on the particle physicist to describe the model or the candidate, right?
Yeah, right. That's why they are there, right? I mean, they have to fulfill a purpose, right? I mean, to create all these nice candidates for dark matter. So weakly interacting massive particles, as you mentioned, is a great class of candidates for dark matter and also dark matter and all the things. I'm really not a specialist of that, so you know better. But yeah, I mean it's a very interesting line of research to invent these candidates. Now, big question for me is when we can actually have experimental data that could really give us more like on this, what could actually be dark matter. But I think we're still really far from understanding that.
If ever. Okay. I don't know if we have any other questions. So I can't see any raised hands. So I guess that's it for our wonderful lecture today. Okay, finally, in the name of the Arab Physical Society and the CTPA, Center for Theoretical Physics and Astrophysics, I would like to thank again Dr. Xavier Dupac for this wonderful talk. And let's hope that this won't be the last time we host you here, and that we will follow up with you, especially with the new results that might come up with the Euclid mission. So let's hope to see you again, Xavier.
With great pleasure, if you want. Thank you so much.
Thank you so much. And good evening, everyone.
Thank you.
And see
Good
you
evening.
next time. Bye for now.
Bye.